Recording is rolling. Welcome to Friday. We're on this Friday right here, so we're gonna do as many of these book problems as we can. Uh, should be able to do about half of those. Okay? So here's the list I gave you guys yesterday, the agenda for coming up next week. You guys know next Tuesday, this upcoming Tuesday, you guys are not going to meet here. You guys going to meet where? Yeah, this room right here, right? The six room, 6127. That's the music building, right? Or building 6. Okay, here's that. All right. And speaking of relocations, some of your other classes might be relocated too, possibly. So, I don't know if you guys can read that or if that's applicable. Hopefully, your other teachers are telling you where you need to go if that's applicable to you. All right. So let's do some book problems. All right, chapter 9. All right, first one, number 55. Bullets. 2 bullets of equal mass are shot at equal speeds at blocks of wood on a smooth ice rink. Ooh, smooth ice rink. I bet they're talking about a frictionless situation. Right? Maybe kind of like that Magic School Bus baseball field, like frictionless. One bullet made of rubber, boing, bounces off the wood. The other bullet made of aluminum burrows into the wood. Oh, guys, bouncing off versus burrowing into. The one that boing bounces off, that's called a what kind of collision? Like elastic, right? Elastic, right? Versus if it collides and sticks, like burrows into, like sticks into, right? That's called inelastic, right? In which case does the block of wood move faster? Okay, so this is a qualitative question. Notice they didn't give you guys any numbers. So I'm going to make a sense of it. So, all else equal, if you got the same mass of wood, let's say same mass bullets too, but just different material properties. So one goes boing, bounces off, the other collides and sticks inelastically. For 55. Right, so let's do a side-by-side comparison of these two. So there's an elastic situation, like bounces off, okay? And there's inelastic, like where it'll burrow into the wood. Okay? Now, elastic, when I'm saying elastic, this might not be perfectly elastic. I'll make a note here. So not necessarily perfect, not perfectly. Okay? Because I might throw you guys some example numbers just to make this a little bit clearer. But let's do, we got this. But like the important thing is that just that it bounces off. So we could just contrast these two situations. Okay? So we got an icy surface. We got a block of wood. Now the block of wood has some mass, although not as interested in the mass of the block of wood as the bullet. Okay? So you got a bullet, mass the little m. Now the little m is the one that I care about. So if I set up an equation or something, okay? That's on the move. Okay, those cases. Okay. Now in the elastic situation, it's going to boing, like bounce off. So it's got some initial velocity headed towards the block wood, but then have some final velocity away from the block, right? Versus inelastic, well, it has some maybe the same initial velocity as the last situation. We're keeping almost everything the same except for the material properties of the bullets. Okay? But it's going to embed itself in the block. It's going to embed itself there. So that V final of the bullet is, well, I don't want to say exactly 0 because it would just match the speed of the block. But if the block itself is extremely massive, right? Let's say like planet size, for example. Like what if you fired a bullet into the Earth or something, right? It would approach 0. So let's just say small. Small but still positive, right? Like still in the same direction. Okay. Maybe even approximately 0. Maybe not exactly, but approximately. Right? All right. So which one is going to send this big old block of wood moving faster to the right? So I'll say V wood post-collision, right? Versus this V wood post-collision. Right. Which one of these values is bigger, right? Elastic or inelastic? Right. So, well, collision going on. Maybe this has something to do with impulse, right? So something like impulse. And isn't impulse like the change of momentum? You guys know change of momentum, impulse, okay, is mass times change of velocity. Okay, right? Because that's what would cause the block of wood to move at all, is that there's some momentum being transferred. Right? There's side-by-side comparison here. Right? Notice I'm telling you it's the mass of the bullet. That's what the little m is for. Whoops, change velocity. Mass of the bullet, right? Because that's where the momentum is coming from. Okay? Now, change of velocity of the bullet, wouldn't that be like final minus initial? So the impulse delivered to the block of wood is the mass of the bullet times the final velocity of the bullet minus the initial velocity of the bullet. Same story over here. Mass of the bullet times its change of velocity. That's the momentum that's going to be transferred into the block. Right? Okay. And let's see if the mass of the bullet is the same in both cases. Maybe even the initial velocity is the same, but the final velocities are different. Okay. And here's where it might be helpful to throw some example numbers on here. Okay. Suppose the bullet was initially traveling at like 100 meters per second, and that's true for both of these. Right. Okay. But here on the right side, it's close to zero, maybe like 5 meters per second or something. Right. However fast the wood blocks move. But on the left side, it's going to boing, rebound, maybe at, well, it could go up to negative 100 if the block of wood is extremely massive, but I did specify that this is not necessarily perfectly elastic, so I'll make up something. Let's say like negative 50 meters per second. I think that'd be a nice round number. I spelled it, makes sense this way. Okay. So, maybe we've got a question that could lead into the question of which block is going to move faster, which is, well, which one had more momentum transferred into it? Right? The one that the boing bounces off, or the one that like sticks and glides? Right? Now, I bet some of you guys are seeing it by now, so let me see show hands. Right? So here's your options. Either the block on the left or the block on the right is going to be moving faster. Right? How many guys think that it's going to be the block on the left, the boing block, is going to be moving faster across the ice? Who says the one where it glides and sticks? Okay, well, let's take a look at these example numbers that I wrote in red. Okay. And think, well, what was actually like change of velocity? Okay. Like the one on the right, yeah, if it approaches 0 meters per second, you guys see the change of velocity of the ball would be pretty close to 100 meters per second. Maybe it's like 90, 95 meters per second change of velocity, something like that. Okay. Pretty close to 100, right? Okay. What about the boing situation? What is the difference between 100 to the right and 50 to the left? What's the difference between 100 to the right and 50 to the left? And it's not 50, it's 150, right? 150? You guys get that? Okay. Let me show you guys this on a number line in case you don't quite see it. Okay. Number line, we got 0 meters per second here. Let's go negative 50 meters per second, positive 50 meters per second, positive 100 meters per second. Okay, so I got a nice number line, right? Keep going forever. Okay. So if the bullet was heading 100 meters per second to the right, and then rebounds, rebounds the opposite way at 50 meters per second. You guys see this delta V right here is actually 100 minus negative 50 is 150 meters per second. Okay. Versus the one that embeds itself, well, it's going to be somewhere in here. Okay. This delta V is closer to 100, okay? Maybe like 95 or something, but closer to 100. Okay, would that be true? Okay. All right. And since these bullets have equal mass, the one on the left, one on the right, then which one transfers more momentum? Gotta be this one on the left. Okay. So this could be like 100. No, sorry. Well, negative 50, final minus initial, right? Negative 50 minus positive 100 would be a change of like negative 150. Multiplied by the mass of the block. Okay. Versus this final minus initial, let's say the final is like 5. Right? The initial was 100. Right? That's only a change of 95. Right? So the one on the left transfers more momentum into the block. Yeah, this block on the left that boing, the bullet bounces off of, right? That's gonna send that block moving faster. So this guy right here is moving faster. This is the faster block. This is the slower block. There's more momentum transfer if you bounce off something than if you glide stick. And it could, let's think about limiting values. It could be up to twice as much, because if the block is extremely massive, and that would be the case, right, then this difference would approach 100 at 95 in this case. And if this is getting close to perfectly elastic, this would be up to a change of 200. So we have 100 here versus 200 here. This one, the bouncing collision, could get up to twice as much momentum transfer. Okay. Next one, number 61, volleyball. A 0.24 kilogram volleyball approaches Tina with a velocity of so many meters per second. Tina bumps the ball, giving it a speed of so many meters per second, but in the opposite direction. Right? Ooh. Hey, are we going to run into the exact same scenario that we've just been looking at? Right? Notice they said, they said one velocity and one speed, right? Because opposite direction. To make this a velocity, you have to make one tiny change. You have to put a what there? Like a negative sign, right? To take care of the direction. So this should actually be like a negative number, right? If you're thinking in terms of velocity. Right? What average force did she apply if you were pointing your hand to the ball? If that collision lasted for this tiny time interval, like a fraction of a second, like LeBoing, right? Fill us out. So this one. This is number 61. Go. All right, so here comes this volleyball. It's got a mass and an initial velocity. Okay. Now I'm gonna make it. I'll keep the mass the same because that's probably like some regulation number or something. Okay. So 0.24 kilograms. Okay. Maybe that's like volleyball. Yes. We said. Yeah. All right. So let's say it's incoming with initial velocity of make up my own number. I'm gonna say 10 meters per second. Okay. And well, I guess I'll make a left negative. So let's say it's coming in the negative direction. Okay. And then here's our hand right here. Okay. And there's going to be this collision. Okay. So boing, it's going to send this volleyball the other way. Okay. Let's say with a post-collision velocity of positive 5 meters per second. Okay. So it changes like that. Boing. Okay. Okay. And there's one more thing you have to know. You have to know the time interval of that collision. So let me just give you guys a very small time interval, like a tiny fraction of a second, maybe a 20th of a second, right? 0.05 seconds. Right. So similar story to before is that if you're interested in the change of velocity, okay, make a number line, just like I did for the last question. If you want the change of velocity on a number line, let's put, say 0 meters per second, 5 meters per second, -5, -10. Okay. If you didn't see before, I bet you guys see now that the change in velocity associated with that bounce is positive 15 meters per second. Okay? And I think because the volleyball is going the other direction, so it would be like a negative number for you guys. Something like that. All right, so let's look. The question was average force, right? So this is an impulse question. Impulse is, it's force times time interval, but that comes from applying it's massive change of velocity, and that comes from applying a force for some time, right? It's all the same, right? This is your impulse formula. If you look at your notes from a couple days back, okay, you'll see this. This is called impulse. Impulse. Right? Change in momentum. That's what impulse is. Change in momentum. And this force represents the average force, and that's what we're solving for. So we should know all these other things. So average force times a time interval of, I told you that right there, this many seconds, okay, is equal to mass of the volleyball that's having its motion change, okay, times change of velocity. Well, you guys see it's going to be 15, but if you want to see the mechanics of that, final minus initial, that'd be 5 meters per second minus -10 meters per second. You guys know minus and negative is kind of like plus. So that's your 15 right there. Here's your change of velocity of 15 meters per second. Okay? Now there's one algebra step to get to the answer, and that's just to divide both sides by this time interval, 0.050 seconds. Do that to both sides to balance the equation, just like we've been doing all year. Little algebra step right there. And what is 0.24 kilogram times change in velocity of 15 meters per second, all in 0.05 seconds? Okay. I'm looking at an average force of 72 what? What's the unit? 72 kilograms, joules, newtons? What is that? How do we measure force? Newtons, yeah, newtons. There you go. Okay. That's what kilogram meter per second squared is, right? Yeah, good call. Newtons. Okay. So, I've got that's all the book asks, but I've got my own additional question about this. What if this volleyball, let's say it was sewed together with some kind of thread that could, it could withstand a punch up to 100 newtons. It's like, as long as the force is under 100 newtons, it's fine, they'll stay together. But if you hit it with a force of 100 newtons, this ball is going to bust open and you'll have a ruined volleyball. Is this volleyball safe? Well, this is 72 newtons, so that's less than 100 newtons, so maybe. Okay. But remember this whole thing about average, like average force? Okay. Let me tell you guys what that's about. I'm going to draw a graph that's, let's do a graph. Okay. This graph is going to be a force versus time graph. Okay. In fact, if you glance later in this on this homework page, you'll see other force versus time graph setups, force versus time, newtons versus second, right? And anytime you see a force versus time graph, let's say some of you guys are going to take physics in college, whenever you see force versus time, think impulse and momentum. Okay? And I'll show you guys why. Okay? So what if you had a slow motion camera trained on this motion here, boing, right, as this volleyball is being hit? Okay? Slow motion camera, what would that look like? Okay? You remember that the time for this whole thing to happen is a very small time interval. You got 0 seconds, 0.05. The whole thing is over in a tiny fraction of a second. Right? Something like that. Okay. All right. Well, is that force constant, like all applied at once? Let's look frame by frame. Okay. So here comes the volleyball. Okay. Moving in this way, and here's her hand. She's going to bump it the other way. Okay. On a collision course, and they just start to make contact right there. So it starts out with 0 newtons of force, okay. But then that force is going to slowly start to build up. Okay. By the time you get to, let's say, the halfway mark, here's her hand, still in motion. Here's the volleyball. You guys ever seen like slow motion footage of like a ball being hit? It's all like squash. Like volleyball, baseball, golf ball, they all kind of look like this. Look at slow motion footage. Right? And then the time interval that the force is applied for, right? Well, at the end of that time interval, now the volleyball is leaving her hand and going the other way. Has some forward velocity like that. Right? So that whole thing, boing, that's what that will look like frame by frame. Right? And what does the corresponding force versus time graph look like? Well, it starts off at 0 newtons of force when there's first making collision, first making contact, collision starts. Right? Then that force is going to build up. Then at halfway point, when it starts to actually rebound, move the other way, okay? That force is going to start to decrease, and it's going to go to 0 again when they lose contact. You guys see that classic triangle-looking shape? Right? Take a good look at the next question we're about to do, 66. Do you guys see a force versus time graph? And look at that, a classic triangle-looking shape. Okay? Because that is actually a better model for how collisions work, right? Because that whole story I told you with like the frame-by-frame breakdown. Okay? Do you guys remember from your notes a few days back what the area of that triangle represents? What physical property? Give you guys a hint. Change of momentum. Impulse is force times time interval, which results in some mass times change of velocity. Right? Oh, look at this version of impulse right here, change of momentum. Force times time interval. Hey, I've got axes that are like force and time. Right? Because if you ever see some graph, like some physics graph, you're trying to figure out what properties does this graph represent what things. Maybe you have coordinates, maybe you have slopes, maybe you have areas. Right? Even if it's some new graph you've never seen before, you can sort of figure it out. You can navigate your way around the graph. This is one of these tools you can pick up from taking the class like this by knowing what units each axis represents. Okay? And isn't the area of any shape something to do with base times height? Right? For a triangle, it's half base height, but something to do with base times height. Okay? Look at that. Base times height. Time interval times 4. Okay, so the area of this triangle represents the what? The impulse, right? The impulse, right? And okay, so how does that compare to like all this stuff? Okay, well, we said average force times time interval would also represent that impulse, okay? But isn't that more like a rectangle shape? Right? Just straight base times height. Okay? So what rectangle would also represent that? Okay. Here's F max. That's definitely not average. That's F max. Okay. What if I turn this into a block of ice, like a big old triangle block of ice? I have some fish tank walls right here, aquarium walls. Let the whole thing melt. Isn't it going to melt down to exactly this halfway level right here? This is F average. That's what we actually calculated. We actually calculated that right there. Okay? But that is F max divided by 2. Guess that? Okay. This rectangle has the same area as that tall triangle that represents the same amount of impulse. Okay? And so you have average force, F average, times this time interval right here. Here's your delta t, time interval, right? That's that rectangle, isn't it? Okay, so going back to the case of what if I told you that this ball was manufactured so it can withstand up to 100 newtons, but anything over 100 newtons is going to bust apart. Does this volleyball bust apart, or does it stay together? If you go up to 100, right? Well, at first glance, it might look like it's safe, but then you think, hold on. This is 72 newtons. So, F max must be what? 144 newtons, right? Or wait, is that right? Yeah. So no, that is not a safe volleyball. Okay, guys ready for next one? 66. Hey, this is a force versus time graph, just like we just did. We got a 0.15 kilogram ball. Pause right there. That mass is extremely close to the mass of a baseball, which you can see in the exact next question. Right? See that? It's almost like exact same mass. Right? Almost. Right? So maybe we'll even call this a baseball. Right? This baseball, moving in a positive direction at so many meters per second, is acting on by the impulse shown in the graph. What is the ball's speed at the say the 4-second mark? Right. So they gave you a time axis that's like way more time than you need. The only part that really matters is from the 1 to 3 second mark period, that, because we're just gonna use that to figure out the impulse, and based on that impulse, you can figure out change in velocity, and then you can figure out final velocity. So it's gonna be sort of a multi-part question. So one piece at a time. So first thing first, we got a force versus time graph. Force versus time. And I'll go ahead and use the time axis just like the book has. Tick, 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 tick. Right. Although these collisions, usually it's a small time interval, but I guess you get out some number of seconds. That's okay, right? I'll change the force axis though. So I'll make this 0, 10, 20 newtons, something like that. Okay. And force versus time, they gave you this type graph. Okay. Now, based on what I just told you with the last question with the volleyball, whenever you see force versus time, you see that classical triangle shape, that classic triangle shape. Okay. You should immediately start thinking, and the gears in your head should start turning. You should start thinking, the area of that triangle represents impulse. Okay. Here's your time interval right here, delta t. Looks like 2 seconds, doesn't it? 2 seconds. Okay. Here's your, height of that triangle. It looks like F max is going to be 20 newtons. F average is 10 newtons. Okay. Okay. So here's F max, height of the triangle. Okay. Impulse is m times delta v, which is also f times delta t, right? which is area of the above triangle. Area of the triangle. Okay? Tell you guys what to. Doesn't this force actually represent average force? Is that okay? Okay, which would actually be like the halfway mark. Okay. This whole F times delta T, that would be like the shape of a rectangle, although they give us a triangle. That's why I'm saying it's the area of a triangle. Let me give you guys the more generic, the more general math way of describing this, okay? Which is as an integral. So this is calculus notation. If you add up the force as a function of time for some time interval, then, well, it's basically just that right there, the area of the triangle. Okay. And so let's plug in some numbers. So we got the mass of the ball is, whoops, got the right mass of the ball, 0.15 kg. Okay. So 0.15 kg times change of velocity of the ball is equal to area of the triangle. Isn't that 1/2 base height? 1/2 times 2 seconds times a height of like 20 newtons. Is that right? Okay. Guys good so far? Okay, so let's figure out change of velocity, and then we'll worry about the actual book question later, which is what's the final velocity. All right, so delta V, isn't that just going to be the triangle 1/2 base height all divided by this mass? So there's an algebra step right there. Hopefully you guys are really comfortable with algebra by this point in the class, because we just use it every day so much. Right? So 1/2 times base times height. Okay. Looks like the impulse was 10 Newton seconds. Or, no, it isn't. 20. Typed the wrong number here. 20 Newton seconds. Okay. That 20 Newton seconds acts on 0.15 kilogram ball. Okay. So that gives it a change in velocity of this many meters per second. Now, I picked force values that are about 10 times your book values, so you probably have a much smaller change of velocity. Okay. Do you guys remember how change of velocity is final velocity minus initial velocity? You guys remember that? Okay. So if you're solving for final velocity, couldn't you just say final velocity is equal to initial velocity plus the change? Maybe that just makes sense just in its own context too, right? Start with something, add a change, you'll end up with some final value. Right, so change of velocity, that's this number right here. Pop that in. So 133 meters per second. The initial velocity, your book gave you some value. I'll make up something myself. Right? Maybe it was like, I don't know, 67 meters per second. I'm just making something up. Right, so that would be what, like 200 meters per second. Okay. Guys good? Okay, so recap that one. You guys saw a force versus time graph, which means that the area that represents some impulse. If you solve for that, take that impulse, divide by the mass, it'll give you change of velocity. And then if you know how fast it was going, and then you add that change of velocity, you'll end up with the final velocity. Yeah. It was given to you. So in the book problem, they told you it was like 12 meters per second. Right. So I just made up a number. One thing about this one too, if that had been referring to baseball, you could attach the story that maybe it was hit by a bat or something like that. But with that particular story, maybe the baseball was headed one way and then the bat, the boing, hits it the other way. Okay. And if that were the case, then the initial velocity and the change of velocity would have to have opposite signs, right? So there'd be sort of a subtraction, that kind of thing going on. Okay. Number 67. This one's labeled baseball. So we got a 0.145 kilogram baseball moving at this many meters per second, and it's caught by a player. Now, caught by a player, that means if you catch a ball, aren't you bringing its final velocity to 0 meters per second? Okay. And to do that, to go have a fastball, this mass, to bring it to rest, you would have to apply a force. Ooh, this is already sounding like an impulse question, right? You're changing the velocity of some mass, and you're applying a force to do that. Question A, what is the change in momentum of the ball? And there's a couple of follow-up questions, so let's just focus on that one first. Okay. Number 67, baseball. So have a baseball, mass 0.145 kilograms. 1 minute. Are we gonna run out of time? We are. Okay, well, I'll get you guys as far as I can get you guys. Initial velocity was, pretty, give you guys numbers that are pretty close to the book numbers. Let's say 30 meters per second, for example. Okay. So when final velocity be 0 meters per second. Okay. So first question, part A, what's the impulse? Okay. Well, you could say force times time interval, and maybe that'll be useful a few minutes from now. But I'm going to use the other version of this, which is this right here. Okay. So the mass is 0.145 kilograms. That's the mass that you're slowing down. Okay. And the change of velocity, well, if it went to 0 from 30 meters per second, that's final minus initial. You guys see it's going to be a negative impulse, right? Because you have to apply a negative force. You have to apply a force in the opposite direction of the original motion. 145 is 30. Right? I'm looking at 4.35. This would be you can call this kilogram meter per second. You could also call that Newton seconds. Right? So that's the answer to part A. Right? Part B, I'll just go over the other parts verbally and then maybe hit these after the weekend. If the ball is caught with the mitt, it's held stationary. Okay, so let's say it takes some time interval for that to come to the top. Time interval. Could you just do impulse divided by time and get the average force? Okay, so that would be part B. Great. Actually, questions B and C are saying about the same thing. Okay, so as far as we get today, all right, you guys have a good weekend, and we'll solve the rest of these on Monday.